CS294-112 Deep Reinforcement Learning. As you might have noticed, the class is pretty full. We have about double the number of students enrolled that can actually physically fit in this room. What that means is that, due to fire code reasons, we obviously can't have 180 people in the room. We do have a live stream that is posted on the course website. In general, those of you that are enrolled in the class, you should just come to lecture, because after the first couple of weeks, many people will be watching the course online anyway. There will be plenty of seats for everybody, but in the first couple of weeks, it does tend to be pretty crowded, so bear with us for that. We do want to enroll as many students as we can so that people who want to take the course can take the course, but sort of the price of that is that we end up with more students enrolled than there are seats in the room. But later on, as the semester progresses, at least based on past years, there will always be enough seats for everybody, so just the first couple of weeks are a little crowded. Okay, so I'll start with a few notes about course logistics, and then I do actually have a real lecture to deliver today, kind of introducing the course material, but I want to start with the logistics just to get that covered. So who are we? Who's teaching the course? This is me. My name is Sergey Levin. I'm the instructor. I'm an assistant professor here in the Electrical Engineering and Computer Science department. We have 4 graduate student instructors and 1 undergraduate student instructor. So our head GSI this semester will be Kate Rakelli, and then the other GSIs are Gregory Kahn, Sid Reddy, and Michael Chang. And some of you might have met Greg already. Greg and Michael are here today. They're kind of just making sure that the room doesn't violate the fire code, basically. And then Sarush is undergrad GSI, who's going to be helping us with some of the material preparation, things like that. A lot of the material that you guys need, course logistics, syllabus, etc., is on the course website. So if you haven't done so already, do take a look at the course website right there. If you type like Berkeley Deep RL course into Google, you'll also find it. There's a Piazza page for the course, so make sure if you're enrolled in the course that you're signed up for Piazza. We try to enroll everybody in Piazza automatically from the class roster. But if you used an email address in Cal Central that's not your actual email address or something, maybe you were not enrolled correctly. So do make sure that you're enrolled in Piazza, because we're going to be using that for all of our communication in the class. We ask that enrolled students who are formally enrolled in the class sign up for Piazza. If you're not a formally enrolled student, you're still welcome to follow along. We'll post all the lectures online. And if you want to have a discussion, you can do that on the course subreddit, which is right here. Office hours, all of the GSIs will hold office hours. They are posted on the course website. We've already selected office hours. My own office hours are immediately after class in SOTA 341B on Wednesdays. I don't have office hours on Fridays, but I do have office hours on Wednesdays immediately after class. And now that Michael and Greg are in the room, they can introduce themselves. So Greg is right over there. Greg, you want to wave to everybody? So that's Greg, and that's Michael. And then the other 2 GSIs, the grad GSIs aren't here, but you can come meet them in office hours, ask them whatever questions you want to ask, and so on. Okay, so that's introductions. Some prerequisites and enrollment information. So this is an advanced graduate level class. It's intended for students that are, its primary purpose is to prepare you for doing research in deep learning and reinforcement learning, and it's really primarily aimed at PhD students. That said, we do have a number of master's students and undergraduate students in the course, and that's great. But you should make sure that you meet the course prerequisites. We require you to have taken a graduate or advanced undergraduate level machine learning course in the past. If you are a student at UC Berkeley, perhaps you'll have taken CS189, 289A, 281A, something like that, or an equivalent course at your home institution. So if you're not certain whether your course, the class you took before fulfills the requirement, just go to like the CS189 website, look at the syllabus there, make sure that all that stuff looks familiar to you. If you're not sure whether the course you took at your home institution fulfills the requirement, just email me. Just tell me like, hey, I went to this university, took this class, here's the syllabus, does this fulfill the requirement? That's totally fine. Please enroll in the class for 3 units. So the way the 294 classes work at Berkeley is they allow you to enroll in between 1 and 4 units. By default, I'm assuming everybody will enroll in 3. If you have some compelling reason to enroll in a different number of units, again, please email me or Kate, the head GSI. There is a long wait list for the course, so especially for undergraduates, we didn't have room for everybody, so there is a wait list. We don't use the official Cal Central wait list. We use a Google form that is linked on the course website. So If you want to enroll in the class and there's no room, don't put yourself on the Cal Central waitlist. That doesn't do anything. Go on the course website and fill in the form. Currently, there are roughly 180 students on that waitlist, and we will be enrolling students as people drop. So even though the class is completely full, in past semesters we've had 30, 40 students drop over the first few weeks because a lot of people are shopping classes. So don't worry, there will be more students getting enrolled, but probably not everybody, unfortunately. But that said, all the lectures will be recorded. We'll post them online. Anybody can view them online, so that's totally fine. Okay, other than the formal prerequisites, what is it that we expect you to know? So the homework assignments in the class, a lot of them will involve training deep neural networks with standard automatic differentiation packages. We don't actually require you to do the homeworks using any particular package, but we provide you starter code, which is very convenient to use, and all the starter code will always be in TensorFlow. If you really want to, if you believe you can do the assignment just by rewriting everything from scratch, you can actually do that, because the assignments only, the main thing we'll be grading is actually your report with all the graphs and results. So you can re-implement everything in PyTorch if you really want to. That's fine. It'll be a lot more work, though. So all of our starter code will be in TensorFlow, and by default, we're assuming everyone will do things in Python plus TensorFlow. But if you want to do a ton more work and do it in some other way, that's okay, although we wouldn't recommend it, and we can't guarantee that we can provide support in office hours for like some weird random automatic differentiation package that you want to use. That said, our GSIs are very well versed in this stuff, so if you are using something else, there's a good chance that one of the GSIs can help you. We just can't promise that. We do expect you to come in with good prior experience programming in Python. We don't necessarily expect everybody to be a TensorFlow expert coming in. So Greg Kahn will actually teach a lecture on TensorFlow and automatic differentiation next week. That said, it's one lecture, so probably if you've never used TensorFlow in the past, you'll have a little bit of a learning curve. But there are excellent tutorials online, and that's something that you can definitely work on this week to get up to speed. And maybe after you see Greg's lecture next week, you'll be in better shape. So we don't expect everybody to have used TensorFlow before, but if you haven't, do expect a little bit more work in the first few weeks as you get up to speed. If you've never programmed in Python before, you might find this class a bit challenging. So if you've really never done any Python programming, definitely a good idea to come to office hours and talk with me or with one of the TAs this week to make sure that you'll be able to get up to speed fast enough. And if there's some reservations, maybe think carefully about that. Okay, what will we cover in the class? The full list of topics for all the lectures is actually on the course website. So if you go on the course website and you click on lecture slides, that's our lesson plan for this course, and you can see what each of the lectures will be on. We might adjust it a little bit as the semester goes on, but that's the current plan. It's already on there. We're going to cover how we basically go from supervised learning to decision-making problems. So supervised learning is hopefully something all of you are familiar with from your prior machine learning course. We'll talk about how that can be transformed into a decision-making problem. We'll talk about imitation learning. We'll talk about the core model-free algorithms, Q-learning, policy gradients, actor-critic, and so on. And we're also going to talk about model-based reinforcement learning and some advanced topics in prediction, predicting video frames, and so on that might apply to model-based RL. We're going to talk about exploration, and here we'll touch on a lot of more recent research on exploration in reinforcement learning. We'll talk about advanced topics like transfer learning, multitask learning, and meta learning towards the end of the course. And we'll have some discussions of open problems. We'll have some research talks towards the end from other reinforcement learning researchers and some invited lectures and so on. So towards the end of the course, as you're working on your final projects, you'll hear about some advanced topics that will hopefully get you inspired about some potential things to explore in your final project. Assignments and grading. So we're going to have 5 homework assignments and a final project. The grading will, basically half your grade will be based on the homeworks, and half your grade will be based on the project. So there'll be 5 homeworks. The first one, which is going to be on imitation learning, it's going to cover some material that I'll actually present in lecture on Friday, and it also doubles up as a kind of warm-up. So if you're a little unsure about whether your Python or TensorFlow knowledge is sort of up to scratch, start homework 1 early and see how that goes. If it goes smoothly, then you're probably in good shape. If it's a really big struggle, maybe come to office hours and discuss. So it's kind of a combination of warm-up plus imitation learning. Homework 2 will have you implement policy gradient algorithms, which I'm going to cover probably next week. Homework 3 will be on Q-learning and actor-critic algorithms. Homework 4 will cover model-based reinforcement learning algorithms. And then homework 5 will be there will be a few choices to be made there where you'll implement one of a few advanced algorithms that I'm going to present towards the end of the course. So there'll be a few different options for what to do for that homework. And then the final project is meant to be kind of a research level project. So those of you that are graduate students that have done some research in the past, think of this as kind of at the level of what you might submit to a ICML or NIPS workshop. So it's sort of a research paper at the level of a workshop paper. It's a good idea to start on that early. We'll have a little bit of structure there. We'll have a proposal stage, so you'll actually submit a proposal about halfway through the course. We'll have a milestone stage. This semester will probably organize also kind of a mini peer review system where students might actually look at each other's proposals and provide feedback, so more on that later. But what you can start doing even right now is thinking about forming groups. So the homeworks will be individual, but the final project you can do in a group of 2 to 3 students. You can also do the final project individually if you like. If you want to do it in a group of more than 3 students, that might be all right, but please discuss with us in advance to make sure that the scope of the project is sufficient. So we do expect that if it's a larger group, it'll be a larger scope. And you're welcome to start on the research project early. So we'll try to get the final project assignment out to you as early as possible so that those of you that do want to get an early start on can do so. If you're working on research on your own that is related to deep reinforcement learning and you think that you can kind of fit that into the theme of the course, that's fine too. So we're pretty flexible about what you do there. It does have to fit with the theme of the course, obviously. Late homeworks and assignments. Because the class is pretty large, we are fairly strict when it comes to late homeworks and assignments, so we do want you to turn things in on time. You get a total of 5 late days over the entire semester, cumulatively over all your homeworks, but if you exceed that, then unfortunately we can't grade your assignments, so do make sure that you get things in on time. And then your homework for today, pretty easy. First, sign up for Piazza. So if you're enrolled in the class and you're not on Piazza, go to the course website, sign up for Piazza, because we're going to be using that to communicate with you and you might miss out on important announcements. Start forming your final project groups, unless you want to work alone, which is totally fine too, but start talking with students in the class to decide on your groups. And if you're not sure about whether you're like really solid on Python or you're not sure whether this TensorFlow thing is a little too complicated or not, check this out. Check out the low-level intro for TensorFlow and see if everything there makes sense. And if it's a really big struggle, maybe consider coming into office hours. And also, those of you that are enrolled in the class should have received an email from one of the GSIs with a license for the Mujoko physics engine, which we'll be using for homework 1. We send that email to the email address that you have in Cal Central. So if that email address is like something you don't check very much, you might not have gotten that email. So maybe look into that. If you really can't find it, email the head GSI about that. All right, so that's all for the course logistics. Does anybody have any questions about course logistics? Yes?
Does the 5 days apply to the project or just to the homework?
The project is going to be due like as late as possible in the semester. So probably, let me just say no, it doesn't apply to the project because we need to get grades in at some point. Well, we're going to have the project due pretty late, so it doesn't apply to the project. It does apply to any intermediate milestone. Like we'll have a project proposal, and yeah, that's the same as any homework. But for the final project, it's just like we need to get grades out. Any other questions? Okay, so let's start on the main topic of today's lecture, which is going to be an introduction to deep reinforcement learning. And what I'm going to start with is a little discussion of, what is deep reinforcement learning or reinforcement learning in general, and why should we care about it? And in particular, why should we care about it now, today? So I'm going to start with actually a bigger question and then kind of zero in on deep RL in particular. And the bigger question I'm going to start with is, how do we build intelligent machines? So how many of you guys know who this is? Raise your hand. Okay, so this is maybe like a little bit of a vintage cartoon sort of thing, but this is a robot that essentially takes care of household chores. Also has quite an interesting personality, but the more kind of pragmatic bit that's relevant to this class is a robot that does household chores, but any household chore in a very flexible way. So one might think, okay, it's a very kind of maybe not a very skilled job, but at the same time something that demands a great deal of flexibility. So you might say, well, you need a very intelligent machine if you want to do all this kind of stuff. And in fact, in fiction and media, we have a lot of examples of kind of the very exciting visions of the future that illustrate what might happen, what might take place if we have intelligent machines that can respond flexibly and adaptively to a wide variety of situations. So you might have, for example, this guy who can, maybe he's designed to be a kind of a medical kind of assistance sort of robot, but is flexible and adaptable enough to be repurposed to fight supervillains or something like that. Or this guy who is an android and can command a spaceship. Or if you're a little more kind of nefariously inclined, maybe you think about this guy here who is, has also a particular mission to accomplish, but has his own ideas about how that should be done. So we have a lot of examples in fiction about kind of potential futures where we have intelligent machines, but I think it's actually a very worthwhile exercise to think about what is missing between kind of the state of technology today and what kinds of things we might need to come up with, what kind of problems we might need to solve to get to machines that look more like this, or perhaps more to the point, act more like this. We can bring things down kind of a little bit back down to earth and think a little bit about concrete examples of intelligent machines that we can or cannot build today. For example, if we'd like to build a big oil tanker that can navigate from one end of the globe to the other, this is actually not that hard to do today. So we can actually build software that will allow a huge oil tanker like this to navigate from one continent to another over the oceans. And it doesn't even require any machine learning. It's, we've had algorithms that are capable of doing this for a very long time. But you would never actually want to have a giant oil tanker like this doing its job without any people on board. You'd still want to have a human crew on board. And the reason for that is that if something goes wrong, if maybe someone needs to go down to the engine room and fix something, tighten some valve with a wrench or something like that, you still need a person to do that. So the kinds of things where current artificial intelligence technologies really struggle are when we have to deal with the physicality, the visual complexity, the diversity, and all these unexpected events that happen in the real world. So it's really about the flexibility and adaptability. The particular kind of calculations, fast reactions, complicated planning, and so on, the kind of stuff that happens in environments that look more like this, is actually oftentimes not all that challenging. And what we found to be really challenging is dealing with the complexity, with the diversity, physicality, visual variety, and so on, which is kind of what you get in situations like this. So the great thing about deep learning is that deep learning provides us with very good tools for handling unstructured environments. Unstructured means that you can't predict in advance exactly how everything will be laid out. For the giant oil tanker, it's not like the map of the world is going to change day to day. The continents aren't going to move on a time scale that's relevant for the planning algorithm for that oil tanker. But the individual arrangement of objects in the engine room, maybe someone spilled some water on the floor or something like that, that's going to change all the time. There's going to be a lot of unexpected and diverse events. So deep learning helps us handle unstructured environments by allowing us to build very large and powerful models that can deal with raw sensory observations. So, for example, you can build a deep neural network model with millions of parameters that can directly read in the raw pixels of an image. So without having to worry about someone else having detected the right features, just feed in the raw pixels and detect what is in that image. So is this a picture of a tiger or a jaguar or a lynx or something else? And you can use these models to detect thousands of different classes in natural images from ImageNet, translate text, recognize speech, and so on. All these tasks that are characterized by open world diversity and variety. So the thing that's hard about speech is not that we can write down the rules of grammar. It's that all people are going to speak a little differently. There's going to be all this variability, and you have to be able to deal with that. Okay, now deep learning by itself helps us process these kind of complex open world unstructured inputs, but it doesn't really tell us anything about decision making. If we want intelligent systems that can make decisions flexibly, like that, the household robot, the android that can fly the spaceship, and the medical robot that can fight crime, you need some kind of mathematical formalism for decision making, because you have to do more than just recognize what's there in the world. You have to actually choose how to act. And reinforcement learning is what gives us the mathematical framework for dealing with decision making. At its core, this mathematical framework is actually very simple. It models an interaction between an agent and an environment, which consists of a loop. That loop basically represents a cycle of time. The agent makes decisions, which we refer to as actions, and the world responds to that decision with consequences. And there's basically two types of consequences that we deal with in reinforcement learning: the observation, which is what the agent actually gets to see after it made the decision, and the reward, which is the outcome from having made that decision. Did something good happen, or did something bad happen, or did nothing interesting happen at all? And the main thing with reinforcement learning, the really important thing, is that the circle continues. So it's a circle that continues to evolve in time. You make a decision, you observe the outcome, you make another decision, you observe the outcome, and so on and so on and so on. Now, the combination of reinforcement learning methods with deep network or neural network representations is actually something that has been around for a very long time. In fact, some of the first big successes in reinforcement learning actually came from the combination of reinforcement learning and neural networks. How many of you are familiar with TD Gammon? Raise your hand if you've heard of TD Gammon before. Okay, so not very many of you. So TD Gammon was actually one of the first really kind of big successes in reinforcement learning when it comes to game playing. So it was basically a program for playing backgammon that was trained using reinforcement learning with neural network representations for value functions. So it was trained with a variant of an algorithm called fitted value iteration, which we'll learn about later in the course. And it could play backgammon at a level that was competitive to kind of advanced amateur or like junior professional players, at the level of like a state champion sort of thing. So not quite, beating the world champion at backgammon, but still a very high level of proficiency. And it was trained with self-play. It played against itself. The basic idea behind AlphaGo, which many more of you might have heard about, is actually very similar to the basic idea underlying TD Gammon. The idea is to combine deep neural network representations with reinforcement learning algorithms in a self-play framework to allow the machine to learn how to play the game. So, this was maybe in the mid-90s. Fast forward about 20 years, and you get something, actually a little more than 20 years, you get something that can beat the world champion at Go, which was previously considered to be an extremely difficult game. Reinforcement learning and deep learning have been combined in many other contexts, learning locomotion skills for simulated robots, learning robotic manipulation skills, playing video games, learning robotic grasping, and so on, many other domains, and I'll show some examples of those in today's lecture. But what is deep RL, and why should we care about it? So one of the ways that I can illustrate the main idea is actually by analogy. I'm going to tell you a little bit about how deep learning transformed computer vision, and then I'll tell you about kind of an analogous transformation that can take place with a combination of deep learning and reinforcement learning. So if you go back in time about maybe 15 years or so and you look at how most computer vision techniques worked back then, they operate on the following formula. Of course, if you're doing computer vision, you're presumably concerned with images. So you start off with pixels in an image, and then you would extract some features from that image. And these features were designed by hand, and actually designing the right features for doing computer vision was very, very important. Like, this was sort of at the level of what somebody might spend their entire PhD thesis working on. You might invent a really good feature and get a big improvement on a lot of computer vision tasks. And usually for more complex tasks, it would be more than just one layer of features. Maybe you extract some low-level features. This is a picture of histogram-oriented gradients, which are kind of edge-detecting sort of features. And on top of those, maybe you might want some higher-level features so that you can actually start detecting more complex principles, like the shape, the pose of a person. So you might use something like a deformable parts model. And then on top of that, you might figure out all the different body parts of a person and put bounding boxes on them or something like that. And the actual learning really just happens here at the end, and it might be some kind of linear detector or classifier. The way computer vision is done today, it might seem on the surface extremely different, but it's not actually all that different in terms of the basic pipeline. It's different in how it's trained. So current computer vision systems based on deep learning still have multiple layers of representation. If you have a deep neural network that's recognizing objects and images, each layer of that neural network can be viewed as a different layer of representation. The big difference is that all of the layers are trained together end-to-end to optimize final performance on the task. So it's not that someone designed the right conv1 filters. The conv1 filters are trained together with the fully connected layers and everything all together to optimize your performance on the task that you actually want to solve. And this has two really big benefits. One is that you don't have to design them manually, so you don't have to spend an entire PhD thesis defining the right features. But the other one is that they're actually adapted to the task at hand. They're the right features for solving this particular problem because they were optimized to be the right features. And this end-to-end training is a really big part of the power of deep learning methods. Okay, so that's computer vision. Now, what about reinforcement learning? In standard reinforcement learning, using a kind of conventional, let's say, linear function representation, you would start off with some representation of your state. Maybe you encode the state of the backgammon game board in some way, and then you have to extract features from it, because simply putting linear coefficients on every bit of state isn't really going to cut it. So you come up with some features. Now, coming up with features in reinforcement learning is actually pretty difficult, because they're features of the state that are amenable to making decisions, to linearly representing policies or value functions, which is actually sometimes a much more counterintuitive transformation than picking out visual features that are relevant for visual recognition. And they also don't transfer as well between tasks as the visual features do. So this takes quite a bit of work. Maybe for backgammon, you consult an expert who knows how to play backgammon really well, and you ask them, what kind of things do you pay attention to when you play backgammon? Is this kind of feature in the board state relevant to you? Is this kind of feature less relevant? If you're playing chess, maybe it's relevant that the knight is in the middle of the board rather than the edge, so you add that as a feature. So it's a very tedious process. Maybe you have to add more higher level features and so on. And then on top of those, you have some kind of linear value function or linear policy. And there it also matters. If you have a policy versus a value function, you might want very different features. So this ended up being a very, very manual process. And for a long time, the deployment of reinforcement learning algorithms in the real world was very heavily constrained by the ability to design the right features that could make simple reinforcement learning algorithms behave well. So the idea in deep reinforcement learning, very much by analogy to this, is that we're still going to have multiple layers of representation. We're still going to have features, low-level features, high-level features. But the big benefit now is that we can train them all together end-to-end, which has those same two benefits. We don't need to rely entirely on human intuition to tell us which features are the right ones, and we actually optimize the features for the task at hand, which means that we're going to have the right low-level representation that helps us make the right high-level decision. Okay, so what does this end-to-end learning business actually mean for decision-making for kind of real-world style problems? Well, if you want to make a decision on the basis of some kind of sensory percept, let's say that you're walking through the jungle and you see a tiger, like you're not sitting in front of a computer and you get an image of a tiger, like you're actually in the jungle and you see the tiger, you need to do more than just figure out that there's a tiger. You need to take some action. And presumably, if you're a human being and you're walking through the jungle and you see a tiger, you need to take some action that hopefully gets you away from that tiger, because this is kind of bad news for you. So a traditional way of thinking about decision-making, for example, in robotics, is to say, well, we'll have a perception system. The perception system will detect that there's a tiger, and we'll have a separate control system that will act on the output of that perception system. It'll say, okay, you've seen a tiger. Let's think a little bit about what that means for your well-being. Choose a course of action that will result in kind of good outcomes, and then execute that course of action. The trouble with this kind of scheme is that you need to have the right level of abstraction right here. So similarly to the story in the previous slide, you're kind of relying on human intuition to build the right representation for what it is that you're supposed to detect, what is it your perception system is supposed to do in the world, so that you can then use that as the basis for the right kinds of decisions. And maybe you care about more than the fact that there's a tiger in the picture. Maybe you care about how far away it is. Is it a real tiger, or is it a tiger on a computer screen? Like, these things have a lot of bearing on what you should be doing. So you could separately design perception and action systems and choose the right abstraction here, but the problem can be simplified tremendously if you actually do optimize the control system jointly with the perception system, because then it's, first you don't even need to know that the thing is a tiger. You just know that, okay, getting eaten is a bad thing and not getting eaten is a good thing. So I don't really care about which particular species of tiger that is. That's going to be little comfort to me if I fail to run away from it. What I care about is certain properties of this thing that are relevant for my reward function, basically. And we can work through a more realistic example of this kind of end-to-end thing in with a few instances of kind of more realistic pipelines that actually exist in reality. This is an example from robotics. I work on robotics research, so a lot of examples I give will be robotics examples. Those aren't the only examples, obviously, but they're just the ones that are most familiar to me. We can work through an example in robotics where this kind of pipeline stuff can become pretty onerous. So if you're building a robotic manipulation system, a robotic arm that can do complicated things in the world, a traditional kind of engineering approach is to pick a set of modules and wire those modules together. And these are some actual modules that you might want to have. You might want to have, you start with observations, obviously, from the robot sensors, And you might want to have some module that does what we call state estimation. State estimation is basically the robotics equivalent of vision. Detect things from your sensors, figure out where they are, maybe put down key points or bounding boxes, or detect them in 3D. So this is kind of the perception. Then you might have some kind of modeling and prediction stage. You say, oh, I see that there is a power drill at this location. I know something about the physics of power drills, so I can make a prediction using this observation that if I move my hand like this, the power drill will do this and this. So that's modeling and prediction. And then once you can do that modeling and prediction, then you have some planning. So now you're going to say, okay, I'm going to use the output of my state estimator and the predictions from my model to plan a course of action that will actually bring about an outcome that I want, that will result in a desired trajectory. And then I'm going to execute that trajectory with some low-level controller, which will actually determine all that low-level stuff, like which voltage and current to send to the motors so that the robot actually moves in the right way to carry all this out. And typically designing each of these boxes is like, it's a big software project or a big research project. The trouble is that you have to select the abstractions between each of those modules. So you have to decide, well, my state estimator is going to predict, let's say, the 2D positions or the 3D positions or something about this power drill. My modeling and prediction thing will make some simplifying assumptions. Maybe it'll assume the world consists of rigid objects and not worry about, let's say, deformable things or fluids or something like that. My planner is also going to make some simplifying assumptions to make the problem tractable and so on and so on. And each of these abstractions actually ends up being violated to some degree. And then the question of how well your system works boils down to the question of, well, how much are these abstractions really violated? So then you end up simplifying things in various ways. You can say, well, maybe the assumptions made by my prediction, by my model are violated less when I move very slowly or something like that. Or the assumptions made by my state estimator are violated less when I live in a world where all the objects have AR tags on them rather than trying to detect them from pixels and so on. So you end up with systems that have various limitations. And when they leave the envelope of settings where your abstractions meet where the assumptions made by your abstractions are satisfied, then performance degrades very rapidly. With end-to-end optimization, of course, you can overcome this by actually optimizing for the final outcome under the conditions that are actually found in the environment. So here's sort of a little example. This is from a research project about 4 years back at this point of a deep reinforcement learning system that also solves the robotic manipulation task. And just like in the examples I had when I talked about computer vision and so on, it also has multiple layers of representation. So this is sort of the little brain of this robot. And it has some layers that essentially do visual processing. So inputs from the camera go into the bottom, outputs from this network go to the joints. That's the sensory motor loop for the robot. And to use a really tortured analogy, you can think of this little bit, the convolutional net layers, as kind of being almost like the tiny, tiny visual cortex of this robot. This is the bit that actually deals with images. Then this is the little bit that puts in some proprioception. And you can think of this as like a little tiny motor cortex. Of course, this is a very vague analogy because the actual capacity of all these parts is a tiny, tiny, tiny fraction of what even the simplest kind of biological brain would have. But the point is that it has these different modules. They're just all optimized end-to-end to enable this robot to perform the task as well as possible. And how are they optimized? Well, they're optimized from experience. So the robot actually goes and does the thing, looks at the outcome of its attempts, and uses that to modify end-to-end all the weights in this network, which changes what it perceives, what it sees, and it changes how it acts on those percepts altogether. Okay, so let's get into a little bit more detail here. So I mentioned that in reinforcement learning, we have an agent that makes decisions, which we call actions, and the world responds with consequences, which we call observations and rewards. So what are some examples of agents, decisions, consequences, etc.? Let's ground this in a few examples that we might care about. If you're an animal, if you're this dog, you have decisions and you have consequences. So your actions might be the muscle contractions. The brain of an animal exists for one purpose only, which is to move its body. That's the only way that it actually interacts with the world. Whether it's making noises, whether it's barking or moving its legs, it all comes down to muscle contractions. So those are its actions. Its observations are what's coming in through its senses: sight, smell, etc., touch. And for this animal, maybe its reward is food. So it wants to get the food. So it's going to execute the muscle contractions that result in high reward, and it's going to use its observations to figure out which muscles to move and how to attain those rewards. So in this case, maybe it learned that if it sits down, it'll receive the food. This guy you know, maybe for this guy, his actions are motor current or motor torque, something that actually actuates the joints. The observations maybe are camera images, and the rewards are like some measure of task success. So if this guy's trying to run as fast as possible, maybe the reward function depends on how fast he's running, and if he's trying to like fight crime as effectively as possible, maybe his reward function is the average level of crime in the city. You know, whatever, you know, it can span the full range from very low level to very high level, but that's just the goal that this agent is trying to accomplish. But the basic formulas can be extended far beyond kind of the more obvious examples. You could, for example, imagine like an inventory management or supply chain management system, where your actions are what do you purchase at the current moment in time. So you submit orders for what to purchase. Your observations are your inventory levels or some other readings from the various kind of sources of data that you can pull in. And your reward function is maybe the profit that your company is making, right? And even though this seems like a very different kind of scenario, the very same mathematical formalism can be applied to that as well. In fact, the reinforcement learning problem is actually a generalization of any other machine learning problem. I picked these out because they're a little bit more physical in nature, but you could also imagine, if you were so inclined, to take a classification problem and reframe it as a reinforcement learning problem. You can say, well, in image classification, your action is the label that you output, your observation is the image pixels, and your reward is high if you classified it correctly and low if you didn't classify it correctly. That's kind of a silly way to solve a classification problem because it's needlessly complex, but you can do it that way. And the point of that thought exercise is to really understand that reinforcement learning actually generalizes many other machine learning problems. And of course, you probably wouldn't actually want to do image classification using reinforcement learning, but you might want to do things like natural language processing with reinforcement learning. You could imagine, for example, translating text where your actions are which word to emit in the target language, your observations are words in the source language, and your reward function is some non-differentiable measure of the quality of the translation. And people have actually done things like that. So the reinforcement learning basically is the AI problem in essence. If you can solve it in the most general form, in the most complex setting, that is the AI problem. And deep models are what allow reinforcement learning algorithms to solve complex problems end to end. So reinforcement learning provides us with the formulas, with kind of the algorithmic framework, and deep learning provides us with the representations that allow us to apply that formalism to very complex problems with high-dimensional observations and complicated action spaces. So let's look at a few more examples of reinforcement learning and deep reinforcement learning in action. This is a policy that learned to perform dexterous manipulation skills, so it's controlling the joints on a five-finger hand. This is actually a simulation of a robotic hand, and it's learning how to pick up a tool and use that tool to perform some action. In this case, hammering in a nail, or grabbing the handle of a door and opening the door. So these kinds of problems are characterized by very high-dimensional action spaces, very complex relationships between the states, actions, and rewards. So it has to perform a very complex series of manipulations before it succeeds at the task. You can also get, oops, sorry about that. You can also get some unexpected solutions from deep reinforcement learning algorithms. So this is a convolutional neural network policy that learned to play an Atari game. This is the game of Breakout. And the cool thing is that after it practices this game for a while, it finds this kind of really neat solution that maybe the person designing the algorithm didn't expect in advance. That by interacting with the world enough, it figured out that if it kind of shoots the ball through this little opening up in the top, it'll actually get many, many points without having to take lots of additional actions. And of course, when you combine deep network representations with reinforcement learning, you can get effective generalization to very complex, very diverse real-world scenarios. So this is an example of a project where robots were trained to pick up objects with a very large amount of different objects used in training. So they're just looking through their camera, trying to figure out how to move their arm to effectively pick up objects in the environment. And if you train them on enough different objects, then they can generalize effectively to the point where you can show them things that they've never seen before. And just from having seen all these other things previously in training, they can figure out, oh, if I see this kind of block puzzle, I need to separate out the individual pieces and pick them up individually in order to succeed from image pixels. And then occasionally, if you don't succeed, then you can actually take some corrective action. So here, I think this one is still successful, but then the next one will actually screw up a little bit, and you can see that it'll take some corrective action. So it can go in, push the thing a little bit, like, oh, that didn't work. Let me just go back in and try again, and then succeed, and so on. And it's not just about video games and robots. So you can apply deep reinforcement learning technology to many other domains. This is an example that I wanted to describe. This is actually from Kathy Wu, who just finished her PhD here at UC Berkeley, applying deep reinforcement learning to a traffic management scenario. So it's a little bit of a simplified scenario, but you can use your imagination to imagine how this might extend to real-world traffic. So this is a kind of a minimal simulation of an environment where you can get traffic jams emerge. So these are going to be kind of simulated human drivers that are all driving in a circle. And when they drive in a circle, they still actually cause traffic jams because some guy will speed up, he'll pull in behind somebody, slow down, slam on the brakes, and then everyone behind them gets backed up. So you can actually get traffic jams in a circle. But now this red car, the red car is actually autonomous, and it's using a policy learned with deep reinforcement learning to try to regulate not just its own speed, but to actually get the whole circle driving with minimal traffic jams. So the red car only controls its own gas and brake, but what it's trying to optimize, what its reward function depends on, is the speed of all the cars in the circle. So what it does is it kind of herds all the cars to get the whole circle to drive at a good speed. And if you run this long enough, eventually it settles into this equilibrium where it's actually keeping everybody moving. Here's another kind of cute example. This is an intersection scenario. So in this intersection scenario, if you only have kind of simulated human cars, they do more or less what you expect. So they'll kind of brake when they get to the intersection, and eventually they start piling up in these traffic jams because they're waiting for all the cars to get through the intersection. But if you have this one autonomous car that's trying to kind of herd them a little bit, that's the red car, the autonomous car will actually wait here, and it will wait for everybody to build up, and it'll do exactly what you expect, so it'll just time it just perfectly so it gets through the intersection after the last car has cleared it. And then it basically goes on forever like this. So this is maximizing the speed. And you can imagine, okay, these are toy examples. You can imagine what this would look like in a more realistic scenario. Okay, so those are some examples. Then the next question is, well, why should we study this stuff now? Why is 2018 a good time to think about deep reinforcement learning? Well, there are a number of things that have taken place over the last few years that make this kind of the right time for deep reinforcement learning technology to really come into its own. First, we've seen a lot of advances in deep learning. You know, deep learning, there's a very simple idea underlying deep learning, which is the idea of stacking multiple layers of representation and doing end-to-end training. But there are quite a few technical details that are necessary to make that idea really work well. And those individual advances have actually made deep learning a very, very powerful tool today in a way that it was not maybe 10, 20 years ago. And we've also seen advances in reinforcement learning, algorithmic advances, advances in our theoretical understanding of reinforcement learning algorithms, and some of these are things that we'll cover, of course, in this course. And then lastly, we've also seen advances in things like computational capability, ability to train very large models efficiently at timescales that actually make it practical for development and research. And the ideas themselves, the very basic ideas, are quite old, and they've been around for a while. It's just that the combination of all of these three factors is what really makes them stand out now. But just to illustrate, you know, how these ideas have been around for some time, you know, you go back to like the late 80s. This is actually, I think, from '89. There were textbooks on neural networks for control that basically proposed very similar basic principles as the ones we'll cover in this course. This is an example from a PhD thesis written in 1993 called Reinforcement Learning for Robots Using Neural Networks that describes as kind of future work points some things that are basically cutting-edge research today, like you know, reinforcement learning can be naturally integrated with artificial neural networks to obtain high-quality generalization, just like in that grasping example that I showed earlier. Experience replay is a simple technique that implements this idea, blah, 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 but experience replay is actually a very basic component of the game playing, of that breakout policy that I showed before. Instructive training instances provided by human teachers resulting in significant learning speed-up. We'll actually cover imitation learning on Friday. Hierarchical learning, that's something that's actually, you know, cutting-edge research today. We might have a lecture about that towards the end of the course when we talk about advanced topics. Reinforcement learning agent can deal with a wide range of non-Markovian environments by having a memory of their past. And we'll discuss using recurrent neural networks to provide memory to reinforcement learning agents. So a lot of the ideas have been around for some time, and part of what has been missing is all, you know, the confluence of all the right factors to make it possible to really bring them into existence in a practically meaningful way. And of course, there have been successes even a long time ago, you know, going back more than 20 years to the TD backgammon work. There were kind of early signs that the combination of high-capacity representations like neural networks and reinforcement learning could actually allow you to solve very difficult problems. And of course, in the last 5 years or so, we've seen quite a few impressive successes from this area. You know, things like learning to play video games with Q-learning algorithms and policy grading algorithms, learning to control robots, and beating world champions at Go. And many of the techniques that were used for these works are ones we'll actually cover in this class. And for some of them, you'll actually be implementing them for your homework. In fact, I think for these, yeah, you'll implement at least half of these at some point in your studies in this course. Okay, now that's kind of the core of reinforcement learning, the basics of algorithms that solve decision-making problems. But there's more than that, actually, to practical real-world decision-making. So what are some other problems that we need to solve to enable real-world sequential decision-making besides just the core problem of going from observations to actions? And there are actually quite a few others. So, for example, one of the things that we often need to contend with if we want to set up reinforcement learning systems that really work in the real world is to go beyond just assuming that there is a given ground truth ideal reward function. So let me explain this a little bit. Basic reinforcement learning deals with maximizing rewards. That's essentially in the reinforcement learning problem statement, and we'll make this problem statement formal next week. But this is not the only problem that matters for sequential decision-making. So we'll cover more advanced topics like learning reward functions themselves from example. So maybe what you start with is not a piece of code that generates reward functions. Maybe what you start with is data, examples of people performing the tasks that you want to perform, and then you want to back out the reward function from those examples. We'll cover techniques for doing that. We'll talk about transferring knowledge between domains. So maybe you've previously solved other reinforcement learning problems that are structurally similar, and you'd like to now solve a new problem very efficiently. People are very good at doing this. Computers are not as good at doing it, but we'll cover some recent methods for that later in the course. We'll talk about learning to predict and using predictions to act, so you can actually learn about the mechanics of how the world works, learn to predict the future, and use that to act intelligently. Let me start with the point about rewards. Rewards are a very basic part of the traditional reinforcement learning formulation, but they're not actually a very simple thing in reality. If you're training a policy to play an Atari game, you have a reward function for that game because the game has a score. You know how well you're doing at all times because that's the whole point of a game. But in real life, you don't have a score. In fact, people often don't know exactly what they're supposed to be doing. They don't know whether a particular thing they're doing is a good idea or not. And even when there is a well-defined notion of success in a particular task, that well-defined notion of success might be very difficult to measure. For example, if you're a person and you want to figure out how to pour a glass of water for yourself, this is a very low-level physical thing. Just figuring out whether you've done that successfully requires you to have some basic perception faculties. You need to be able to look at the world and understand, is the water in the glass or in the jug? Is it at the right level, and so on. And these are not actually very trivial things to do using just your senses. In fact, sometimes the problem of figuring out whether you've achieved the task perceptually is just as hard as actually achieving it. You could say that, well, we'll just back everything up and say, well, there's some very fundamental reward signal, like maybe the child here is thirsty, so he'll receive reward when drinking the water, not when actually pouring into the glass. But if you take this to its extreme, then you end up with extremely, extremely difficult reinforcement learning problems. Reinforcement learning problems where you essentially almost never receive reward, and therefore you don't have a lot of signal to learn from. This is a quote from a paper written by actually some researchers here at Berkeley that says, as human agents, we are accustomed to operating with rewards that are so sparse that we only experience them once or twice in a lifetime, if at all. Now, this is actually posted on Reddit, and the person quoted this from the paper and then wrote, "I pity the author." So you'll all receive rewards more frequently in the class than once in a lifetime. But there is something to this. In the human brain, at least, there is people have some decent ideas about where the reward signal actually comes from. It comes from this bit, the basal ganglia, and just looking at this kind of anatomical picture, it's like a pretty big thing. It's like a decent chunk of your brain, and it must be doing something to generate the right reward signal to allow you to learn to do interesting things that are actually valuable for your existence. So it's not just some kind of ground truth little switch that flips every time you eat a delicious meal or something. There's something pretty complicated going on in there. And if you imagine the kind of things that animals can learn to do in the wild, if you're a cheetah and you need to chase down the gazelle, if you rely on a reward every time you actually successfully caught the gazelle and then what that means is that until you catch the gazelle randomly just by like flailing your limbs around, you won't realize that catching gazelles is a good thing for your existence. So that seems like a pretty unlikely scenario because the gazelle is actively trying to avoid you. So if you just randomly were walking around hoping you stumble on a gazelle that you can eat before you learn that chasing gazelles is a good idea, you wouldn't live very long. So there must be something a little more elaborate going on. And in fact, people are very good at doing certain things that relate to inferring intentions. You can view a reward as a kind of intention. People are very good at inferring, for example, what the rewards of other agents in the environment might be. You can watch a person doing something, and you can figure out what they're trying to achieve, and you can also imitate them. So you can learn from demonstrations. You can directly copy observed behavior, perhaps without even initially realizing why that behavior is a good idea, just thinking, oh, this guy seems to know what they're doing. Maybe I'll just imitate them and see if something good comes out of it. You can more intelligently infer their objectives and then try to accomplish their objectives in different ways. You can say, oh, this person is trying to reach this destination. I know how to reach the destination even faster. I'll just go and do that first. You can learn from observing the world. You can figure out how the world works, learn to predict events in the world, and then use that prediction to plan ahead. You can do unsupervised learning to figure out good representations of the world without actually achieving any particular objective in the process, and then use that to achieve objectives later on. And you can learn from other tasks. You can make analogies to other experiences you've had to help you figure out new problems more quickly. So you can do transfer learning. We're going to cover something towards the end of the class called meta learning, where you actually learn how to learn more efficiently from past experience. Here are a few examples. This is from a work from NVIDIA research on imitation learning for driving. So the idea here is that you observe a lot of data of human drivers and then figure out how to drive using camera images. And this is just their demonstration video showing their car doing autonomous driving just from imitation. So here there's actually no reward signal at all. There's just data of people doing the task that you can use to copy their behavior. Now this system is directly imitating, so it's not actually trying to reason about what the objectives of the demonstrated skills are. It's just basically doing what it saw before. People can actually infer objectives too. So this is a little video that I think illustrates this very nicely. So here, this is obviously from a psychology experiment, as you might have guessed. This guy is not actually terribly incompetent. He's trying to make a point. But the child here is watching what he's doing. And now the child is not actually going to imitate him. The child is paying attention, and the child understands how the world works. So what the child is going to do, visually it looks nothing like what the guy was doing. But because the child understands the objective of the task, you can actually perform something that's much more useful. And we'll actually discuss in this class algorithms that can allow behavior of this nature to emerge. Obviously not quite this complex, but here's a video of a simple example. Here, there's a human demonstrator who's showing this robot, here are some things that you can try to do, and the robot is watching this behavior and not just trying to directly copy the motion of the arm, but actually trying to figure out what are the potential goals in the world. And here the robot can notice that, well, every time you made me put this orange cup over the yellow cup, it was always the yellow cup that was in that place, so maybe something about the yellow cup really matters. So if I put the yellow cup in a new location and put some, in this case, some nuts in the cup, the robot can actually figure out that, okay, this means that I need to pour the nuts. So it can infer the objective and then re-optimize that objective in a new situation with reinforcement learning. Sometimes better than others. Prediction. Predicting how the world is going to evolve in response to your actions. There's very good evidence that a lot of what we would ascribe to intelligent reasoning in humans is actually based on prediction. The idea that we predict the consequences of our motor commands has emerged as an important theoretical concept in all aspects of sensory motor control, and that makes perfect sense, because if you can predict what's going to happen next, conditioned on your current observations and actions, then you can plan. You can actually plan for things that you've never done before just by using your understanding about how the world works. And we'll discuss how we can do this when we cover model-based reinforcement learning. If you can build a very good predictive model, you can actually do some pretty impressive stuff. And one of the ways that we can find out just how impressive that stuff can be is we can look at work that assumes knowledge of a perfect model. So if you're acting in simulation, you can use the simulator as a perfect model of how the world works. You can try doing all sorts of stuff with that, and that gives you kind of an upper bound on what you can hope to achieve if you learn a model. And if we look at what people have done with kind of known ground truth models, it's actually pretty impressive. This is some work from about 3 years ago from Igor Mardac, who showed that at least in a physics simulator, you can train virtual characters that will walk to locations that are designated by the user. So here the user in real time is controlling this little target, and the guy is walking to that location. This is trained with a policy search method based on trajectory optimization. And we'll cover some things like that later on in the class. You can, of course, learn to predict also. So these videos I'm going to show are from some work by Frederick Ebert, who did experiments on robotic learning where he had robots interact with their environment and then actually record their experiences, record the images that they saw and the actions that they executed, and then use that data to learn to predict future images. So if the robot pushed around some objects like this, it learned something about the physics of the environment, it can actually go ahead and make predictions. It can say, okay, if I'm seeing some particular image, and I take a certain sequence of actions, what will I see in the future? So what you're seeing in these two rows are different predictions. Each column is for a different action, and each row is, starts from the same initial image. So you show the robot an image, you give it a few different candidate actions, and you ask it, predict what will happen, predict what the world will look like if you take these different actions. And if you can solve that kind of prediction problem, then you can actually pick the action sequence that results in the predicted outcome that you actually want to see. So if you'd like the robot to push this little disk to the right, for example, maybe picking this action is good because here it actually predicts that the thing will move to the right. And you can use this to actually act in the world again. So here, for example, the user asks the robot, move this stapler over here. The robot imagines that if it reaches out and grabs the stapler, it'll effectively move it, and then it can go in and execute that behavior. Okay, so you can do prediction, you can do planning. All right, so that's kind of maybe the more practical stuff. In the remaining 20 minutes or so of today's lecture, I want to actually pop up one more level and talk about maybe a somewhat higher level view of why it might make sense for us to study deep reinforcement learning. And it ties back to something I mentioned in the beginning, which is how do we build intelligent machines? If we really go back to kind of the sort of the axiomatic formulation of the problem, think about what it would really take to build intelligent machines, we can start thinking about maybe which ingredients we need to develop. So imagine that you have to build an intelligent machine. Where do you start? Well, maybe you start thinking about an intelligent machine that already exists, like a person, and think about, well, what are the different parts that make up a person's brain? Can we just replicate the functionality of those parts? People need to see, they need to hear, they need to move, all this, they need to have language. So maybe for each of those individual parts, we can write a little bit of code that emulates the behavior of that part. And maybe you go back to a long time ago, you have a very silly model of how the brain works, of what the parts are. You look at what we understand about the brain today, we know a lot more today, maybe we have a slightly better idea of how the different parts work. So maybe we can go in and write some code to implement each of those parts. Unfortunately, that ends up being very difficult because each of the parts solve a very complex problem, and there are a lot of them. So if you want to manually engineer the functionality of each of those parts, like in that robotic control pipeline I showed earlier, that's going to be a huge amount of work. So maybe we can make our lives easier if a particular hypothesis is true, and that hypothesis is that learning is the basis of intelligence. We don't necessarily know that this is true, but we can hypothesize it. And it's a very convenient hypothesis. One of the reasons that this hypothesis might be true is that there are some things we can all do very well, like walking, for example. So maybe it's not unreasonable to think, oh, you have a part of your brain that does walking. But there are some things that we can only learn to do because we can't possibly have been sort of born with those abilities. There's no way that you were born knowing how to drive a car. It's something that you learn to do. And you can learn a huge variety of things. And some of the things that you can learn to do are very, very difficult. So perhaps from this you can conclude that your learning mechanism is likely powerful enough to do everything that we associate with intelligence. Even if there are some things that you're sort of built to be able to do very well right out of the box, there's enough stuff that you can learn that actually that's the stuff that really matters. That basically if there's some kind of difficult problem to be solved, your learning mechanism is powerful enough to go and solve it. It might still be very convenient to hard code a few really important bits, but if the basic functionality is powerful enough, maybe that's all we really need. So then maybe we don't have to worry about writing code to implement each of the little parts of our machine brain. Maybe we just need to implement the right kind of learning algorithm that can learn the parts of the machine brain. And maybe, just maybe, there is a single algorithm or a very small number of algorithms that are sufficient to accomplish this. Now this is a step above the previous hypothesis, saying that not only is learning the basis of intelligence, but that one or a very small number of learning algorithms might be the basis of intelligence. It's a non-trivial hypothesis. It might not be true. But there is some evidence in favor of this hypothesis. So while you could design an algorithm for each module, maybe you can build a single flexible algorithm. And some of the evidence for this hypothesis deals with the flexibility of different parts of human and animal brains. For example, when it comes to perception, you can actually repurpose different parts of your brain to solve different perception problems. For example, you could build a little electrode array, put that electrode array on your tongue, attach it to a camera, and you can actually recover a pretty decent degree of visual acuity from that electrode array on your tongue, even if your eyes are closed, which means that something that your brain does as far as visual processing can also take in touch sensing from your tongue. People can learn to use sound to figure out what's going on around them in their environment. And if you want an example of a somewhat more invasive experiment, this is an illustration of an experiment that was actually done with ferrets. This is sometimes referred to as the ferret rewiring experiment, where what the experimenters did is they took the ferret's optic nerve, surgically disconnected it from the visual cortex and reconnected it to the part of the brain that is associated with sound processing. And this was done to a very young ferret, which was then raised, and then they tested the ferret's visual acuity, and they found that actually, given enough time to adapt, its brain can actually learn to process the signals coming in through the optic nerve using the auditory cortex, which means that whatever machinery was learning how to process that information in the visual cortex might also exist in the auditory cortex, which is like somewhat circumstantial, but perhaps convincing evidence that the same basic principles are at play in different parts of the brain. Okay, so if we for a minute suspend disbelief and say that let's assume this hypothesis is true, what must this single algorithm be able to actually do? Well, it has to be able to interpret rich sensory input, because our agents are going to inhabit a complex environment where they have to deal with senses like vision and hearing and touch and so on that are very high bandwidth, that are very complicated, that entangle lots of different factors of variation. And they have to choose complex actions. They have to actually choose how to act so as to bring about desired outcomes. So why deep reinforcement learning? Well, because the deep part is what can allow you to process complex sensory inputs. It can allow you to take in images, sounds, etc., things that are difficult to interpret with manually designed features, and can also compute really complex functions. And the reinforcement learning is what gives you the mathematical formalism to reason about choosing actions. And there is some evidence in favor of the basic principles underlying deep learning having some applicability to how at least sensory processing in the brain works. Those of you that are interested in this topic might choose to check out this paper by Andrew Sachs, where they looked at the statistics of features learned by deep neural network models and the statistics of features observed in the sensory cortices for different senses in animals. For example, if you look at visual sensing, you can get some idea of the statistics of features that the visual cortex pays attention to. In this case, I believe it's in cats, by exposing them to very structured stimuli. So if you show them vertical bars, horizontal bars, spirals, and so on, you can basically deduce what the underlying features might be by looking at neuron firing rates. And you can do the same thing to artificial neural networks and see if the overall statistics match, if the frequency distributions and so on. You can do the same thing for audio. You can look at sensitivity to different frequencies, different sound patterns, and so on. And again, same story, that the basic high-level statistics of the features match. You can even do it for touch sensing. So for touch sensing, the way this experiment was done on animals is there was a monkey, and the monkey had its hand sitting on a rotating drum with a particular pattern of indentations in the drum, so you know exactly which touch signals it's being exposed to. And for the person, they used a glove that was dusted with some material, so the person would manipulate some objects. They would get the glove, the dusting would indicate which parts they touched, and they would train the deep neural network on that data. So that gets you touch features in a neural network and touch features in animals. And again, you can compare the statistics of those and find that there's a decent match. Now, this is a little bit of a controversial experiment, because then, of course, the obvious question this raises, well, does this mean that whatever weird deep neural network they used here works just like the brain does? Well, probably not. And in fact, the particular type of neural network they use now is something that almost nobody uses, which is called a deep belief network. We don't actually use those anymore. But maybe the more interesting hypothesis is not that there's anything special about the deep neural network, but that there's something special about high-capacity models. That once you have a model that can represent sufficiently complex functions, it naturally arrives at features that have statistics that are good for processing real-world information. And it's really about having high capacity, having enough weights, enough layers, rather than a particular choice of neural network design. And the reason that the features observed in the brains of animals reflect the statistics of those observed in the neural networks is simply because both of these are very high-capacity function approximators, even if their actual design might differ. All right, some evidence for reinforcement learning in the brain. There's also a huge amount of work analyzing reinforcement learning as a model for decision-making and control in animals. And this is, in fact, reinforcement learning actually emerged as a study of animal decision-making and only later on made its way into computer science as a formalism for decision-making for machines. Percepts that anticipate reward become associated with similar firing patterns as the reward itself. So that means that if you see something and you learn that this particular signal always precedes some reward, then you associate that signal itself with reward, which looks an awful lot like something called a Bellman backup, which we'll study later on in the class when we talk about value functions. The basal ganglia appears to be related to the reward system. There are a lot of studies analyzing that. And also model-free RL-like adaptation is often a good fit for experimental data of animal adaptation. So if you actually study how long an animal takes to adapt, what kind of mistakes it makes, and so on, that fits very well into computational models of model-free reinforcement learning, but not always, and it's probably not the only explanation or the explanation of the entirety of the process. So there's probably some more details there. Maybe model-based reinforcement learning has something to do with it. Okay. So that's maybe some of the good news, seems like maybe the parts are there, maybe this is a good thing to study. So what can deep reinforcement learning do now, and what can it not do? Well, there's a lot more left to do. So current deep reinforcement learning can do a pretty good job of acquiring a high degree of proficiency in domains governed by known simple rules, things like board games or video games, where it's sort of a closed world. You know the rules that govern that world. You can generate huge amounts of experience and learn your policies. You can learn simple skills from raw sensory input given enough experience, things like the robotic grasping example, like the one I showed before, basic manipulation skills. And you can learn from imitating enough human-provided expert behavior, like in that driving example I showed before. And of course, we'll explore a lot of these things in more detail in the rest of the course. So what has proven challenging so far? There's still a really, really huge gap. One of the things that's really huge is that humans and animals can learn and adapt extremely quickly, way more quickly than what can be explained by current computational methods. So deep RL methods are usually pretty slow. There's been quite a lot of research in trying to make them faster, trying to make them more efficient, often by reusing knowledge from past experience, and we'll cover some of that in the class, but this is a really big open problem. So humans can reuse past knowledge. It's often not clear what the reward function should be. So if you're going to say, well, my reinforcement learning algorithm is a model of decision-making, well, for which reward function? Because that's going to have a huge effect on how this method actually learns, what it does, and how long it takes to do it. And it's also not clear what the role of prediction should be. Like, is model-free reinforcement learning the way to go? Is model-based reinforcement learning the way to go? Are they actually the same thing? Are they kind of doing something similar? All these things are open problems right now. But the basic idea, and the thing that I really want to make sure I get across in today's lecture, is that one of the things we can start to do with deep reinforcement learning is we can think about building intelligent machines in a way that goes beyond the idea of chopping up the machine brain into parts and implementing the functionality of the individual part, and more towards specifying the right objective and designing a single, relatively simple algorithm that can be very general and that can capture a wide range of different behaviors and different adaptation and learning scenarios simply through the interaction between a general learning algorithm and the environment. And this idea might seem a little bit radical, but it's actually very old. It's basically as old as the field of computer science. So this is a quote that I like very much. Instead of trying to produce a program to simulate the adult mind, why not rather try to produce one which simulates the child's? If this were then subject to an appropriate course of education, one would obtain the adult brain. This was from Alan Turing. All right, so that's it for today's lecture. I'll see you all on Friday when we're going to talk about the first class of algorithms for learning decision-making, which is going to be imitation learning. And I actually have office hours right after this in SOTA 341B.